Hello everyone, so this video is going to be on Autograd in PyTorch. So I would say that if you haven't watched the last video, please go and watch that first because this is going to be based on the last video. In this particular video, we are going to cover three things. The most important one is backpropagation because this actually forms the base of entire PyTorch and why we are using PyTorch in the first place. The second and third one, grad function and grad, I mentioned in the last video also that we will be using or seeing this in this particular video. So before I get started, please go to my Fiverr page if you want to have a one-to-one discussion on projects or just anything in computer science. You think that I'll be able to help you in some of the things related to computer science. So please go and um, approach me. It's very cheap. It's just $5, and yeah, the link is in the description. Okay. So I have changed the equation a bit. This equation has been taken from the official Autograd PyTorch documentation because number one, it's very small and we'll be able to fit the entire thing in one slide, and it actually explains all of the things. Okay, so if you remember, this one, the top one is the forward propagation graph. I'll explain what this is. Okay, so this was the equation. If you remember in the previous video that a big expression was made into smaller expressions. So this is a big expression. It has a log and has a multiplication sign, which means there are two operations. So PyTorch will try to make it into singular expressions. So the first expression is v equal to x and y. V is a variable, like in the last case it was t1 and t2, which PyTorch itself gives. Here you have another variable which is given by PyTorch. We haven't specified it, which is v. And then obviously you have the second equation, which is w equal to log of v. So this is something w has been given by us over here, you can see, and then v is the internal PyTorch variable. Now let's try to make a computational graph as in the last video. So obviously you have these independent variables which we know are the leaves. So x dot is leaf is true, and the first things that happen is you have a multiplication. The input is x and y, and then there is a multiplication. After that you get an output which is v, which is the intermediate variable, and then there is a second equation which is the log, and then when you do the log operation over v you get w, and then I said in the last video that PyTorch adds another variable on itself which is equal to w. So here you can write z equal to w. Okay, so this was our forward propagation graph. Okay, or yeah, forward propagation graph. What you see in the down figure over here is the backward propagation graph, which is, or the backprop graph, which is going to be the topic of our video. I am just showing it here so to make a point that it is almost similar. And if one thing that you want to keep in mind here is, you see z was the last added parameter by the PyTorch. So z was the last in the forward computation graph. You see all the variables x, y, v, w, variables, not operations, have been differentiated with respect to, I mean, z has been differentiated with respect to these variables, assuming every other variable to be constant. Okay, so you see dou z or dz by dx, dz by dy, dz by dv, dz by dw. What is z? Z is the last variable. So if you remember in the logistic regression, linear regression, we used to write z loss dot backward. So obviously PyTorch added one extra variable after loss. So loss was somewhere over here. PyTorch added one extra variable loss over some extra variable here which was equal to loss, and then with that it found all the gradients. Okay, so remember, this is how gradients are showing. Now we will see exactly how this happens from the next slides. Okay, so now we have come to this slide. So this was our expression and we had broken it into two smaller parts. So what happens is, firstly this particular expression will be evaluated. So what happens is, when this one is evaluated, our computational graph is like this. So I am showing how exactly step by step the forward computational and backward computational graph is created. Okay, in the last slide we saw the whole computational graph. Here we are actually seeing how step by step PyTorch creates it. So what it does, it takes the independent variables and it does the first expression. What is the first operation is the multiplication, and you get y. Simultaneously, as this was happening, PyTorch itself created a backward graph. So let's say if this was our entire computational graph, assume, let's say for a second, then this one would have been our entire backprop graph. Why? So the operation was multiplication. Here you have the derivative of multiplication, and what you have over here is dv by dx. So whatever was final, let's assume that in our case v was final up till now. So our differentiation of v with respect to x and differentiation of v with respect to y. Now one thing, if I should not forget it, that why we are doing this, these are the ones that you will be using in the gradient descent. If you remember gradient descent, there is a video in this particular channel on optimization and gradient descent. You can go and have a look. This is actually that we are going to use in the weight update rule. Okay, so and you multiply it with a learning rate and then you subtract it from the old weight to get the new weight. So these are the things. Now obviously we will be adding some more things in the computational graph, so these are not final. However, what I'm trying to say is, as soon as a computation is done, PyTorch, okay, as soon as a computation is done, PyTorch makes all these calculations by itself. It sees, okay, multiplication has been done, so I'll use a multiplication derivative. Now PyTorch already knows the derivatives all this of the simple equations. It knows the derivative of log, it knows the derivative of multiplication, addition, subtraction, division, exponent, everything. Whatever expression you can, whatever operation you can think, PyTorch already knows the differentiation of that. So as soon as you use the operation, PyTorch will make the derivative in its backward graphs. This one graph is different, and simultaneously this graph will also be created. Okay. Now after this, what we did, we added the log equation. We added the log operation and then we got w. Now as soon as the graph grows, backward graph also grows. So what happens? Now it says, okay, on v you got a log expression. So okay, so I will be having a log derivative over here. And now you see what we got after that. We got w. So all these variables now have their differentiation with respect to w. So this v and v are now removed because we know that graph has been expanded. So obviously now these are not the ones that we will be looking for. What we will be looking for is z, because we will be looking for is w, because till now w was found. Up till now this much has happened. So we have all the derivatives with respect to the last node, that is w. Now you see multiplication derivative is here and log. Now I'll show you why these lines are over here. Okay, I'll explain it in the final one. Now we know that PyTorch adds one extra variable which is equal to the last variable. So now what you need to do is you need to find the derivatives of all these variables x, y, v, w with respect to the last one. In the last case also, what was the last variable? W. In the before that case, what was the last variable? V. So all our derivatives were with respect to V because it was last. When the graph was expanded, our last became W, and all the derivatives were of W with respect to the individual variables. I'm kind of getting because it's easy saying derivative of W, but no. Yeah, derivative of W with respect to X. So you find the point, right? You understood the point. So the last variable now is z, and all of these will be differentiated. All of these will be now differentiated, and our numerator will have d of z. Fine. Now this is our final one, but because after this there are no more expressions, there are no more operations, and hence this is going to be our final. Yes, this is going to be our final backward computational graph. Now I'll tell you why these lines are there in a second. So as you can see, this is our full backward backprop graph. This can be used, and you can see dz by dx, dz by dy, and all of the variables, even the internal ones, are being and the final variable is being used to differentiate them. Okay. Now we will see how this backpropagation will work after this. So I've added the z equal to w over here. Now what will happen is, since now you need to find these values, till now we just know dz by dw, but if you remember, we have initially we used to put torch.tensor x equal to torch.tensor, and for x we used to put 3, for y we used to put, let's say, 5, whatever we used to put. Okay, so now what we need to do is we need to find the particular values. Now we know z equal to w, and we need to find dz by dw. Obviously if the z equal to w, will have the differential as 1. The differentiation will come as 1. So we got the value of dz by dw, and the value that we have got is 1. Now what we need to do, we need to find this. Now this is chain rule. Why? it is doing backward. We straight away cannot find this because we need a dependence. We have a dependence over here, so we are able to find it. Now for that we need another dependence. I'll show you how. Now let's say we need to find this one. Now focus on what are the things that I'm telling. Okay, we need to find dz by dv. We know from chain rule, again chain rule is back propagation. We know from the chain rule that dz by dv can be written as dz by dw over here into dw by dv. Fine. Now what we know is dz by dw was equal to 1. Dz by dw, look over here, is equal to 1. Now what is the expression that combines v and w? This one. So can we use it? Yes. So what we will get if we differentiate w with respect to v? Now I told you PyTorch already knows all the differentiations of the simple functions that it uses in the graph. So it knows the differentiation of log. It knows it is 1 by v. So what it will do is, now to find dz by dv, you need to have this which is equal to 1 and this which is equal to 1 by v. So 1 into 1 by v is just 1 by v. So you see now we are able to find this. Now v value, if you remember torch dot tensor 3, whatever v can be calculated x into y, and then you can get it. Okay, now let's take it a step further. Now let's say we need to find the final derivatives. Okay, now to find dz by dx, obviously we cannot directly find it, but given these equations we can say, okay, dz by dx can be written as dz by dw because we have an equation that relates them, and we also have a value. Now after for that, now to do the next step we need dw by dv, because in this graph v came after before w v came, and before v x and y came. So we need to find dw by dv. This equation will help us do it, and we also know the value. Now after that what we need is dv by dx. Now this equation will help us in dv by dx. Now we know dv by dx equal to y. So can we get it? Can we get the value of dz by dx? Yes, we will substitute. So dz by dw equal to 1, dw by dv equal to 1 by v, and dv by dx equal to y. So it will be 1 into 1 by v into y. So that is, I have removed the 1 by v into y. Similarly for dz by dy, you need dz by dw. From here you can find the value which is equal to 1. Then you need dw by dv. From here you can get the value, and dv by dy, from this particular equation you know the value is equal to x. So you can see 1 by v into x. I hope you can see it's 1 by v into x. Okay, so now we have found all the derivatives, which means now we can use gradient descent, because now we know how we have already got the values. So you can say, okay, whatever v will come, we will let's say 3 into 5. So if x is equal to torch dot tensor 3 and y equal to torch dot tensor 5, so x into y, that is 3 into 5, that is 15. So 1 by 15 into what was the value of 5? So that it becomes 1 by 3. So you found the value. Okay, now you know how to do it. So what we will do next is, okay, one thing that I did not write here is, after this we will do z dot backward, and all of these values just you have seen now will be populated. Okay, before z dot backward these values will not be populated, only this graph will be made, but values will that dz by dv will not be equal to, it will be equal to null until then. Only when we say z dot backward, then all of these value will be filled. And how it will be filled, I have told you, it's through back propagation, which is the chain rule. Essentially back propagation is chain rule and nothing else. Okay, so I hope the entire back propagation was clear. You can rewind and see if something was missing, and you can go to the comment section and ask if you didn't understand, or go to my Fiverr page and like if you want to get a very in detailed explanation, and then go to my Fiverr page, because we'll have a one-to-one discussion there. But if you just want to clarify a single question, or you want others also to help you, write it in the comment section. Now I told you we are going to use two functions, and these are actually going to help us. Now first is grad function. You remember two of them I had left, grad function and grad. Now we are getting into it. Now what is grad function? Grad function is nothing but these log derivative, multiplication derivative, basically the derivative of the operations. What were the operations? Log was an operation, multiplication was an operation. So the derivative of that will be grad function, basically nothing else. Now with whom will be these be associated? It will be associated with those which are not the independent or leaf. So we see W was found out by using, or V was found out by using independent variables. So V dot grad, grad function can be used. I haven't written over here, but it can be used. And what will be the value of that? Multiderivative. Why? Because when you say V dot grad function, it will see, okay, how, now listen to this very carefully. How was V calculated? What was the operation that led to the creation of V? Then it will say, okay, multiplication operation was the operation that led to the creation of V, and hence the derivative, grad function of that will be multiderivative. Okay. Similarly, what was the function that led to the creation of W? Then PyTorch will see, okay, log was used to create W. Then the W dot grad will be log backward, log or log derivative. Now the question will be, okay, what was used to create X? Well, there was no expression used to create X. X was just an independent variable. So the grad function will be none. So I'm going to again repeat it. If a variable has been created through a operation, it will have some grad function. And what will be that grad function? That operation itself. However, the independent variables x and y, they were not created by using any operation. They were initialized. So they will have grad function equal to none. Fine? Great. Now grad, the last one, grad. So you know the grad function. What is grad? It is nothing but, now grad function was all for non-leaf variables. Remember this, grad function was for non-leaf variables. Grad is for the leaf variables. Why? Because at the end of the day you will have to update the weights only for the ones that you initialize. You are not going to update the weight of V, because it was an internal node. You did not create it, and hence you don't have any business updating those nodes. Now what you see, these were these were your x and y which were independent, and hence they will have grad, because you need to update these weights. So you can write w dot grad, which is this one, which is not a leaf node, and hence you'll get none, because you don't need to differentiate this. Don't need to update the value, because this was not a leaf node. However, x was a leaf node, and then you can use 1 by v into y, which is the one which is exactly the grad. What is the grad value? 1 by v into y, which we calculated it to be 1 by 3. Okay. Now these lines that I have almost forgotten to explain. Why? Because to just see, if you have to find 1 by v, you need to know the value of v, right? And that's why the value from the forward graph has been passed to backward graph. These are nothing but passing the value of v. This is passing the value of x, because to find this you need the value of x, right? To find this you need the value of y. Where you'll get the y value from? You'll get it from the forward graph. Where you'll get the v value from? Here. So all these value needs to come from the forward graph, and hence you have these kind of lines. Okay, I hope I was able to explain it. I think there's nothing more. Yeah. Okay, now let's implement the 4 functions that we saw in the slides. So for that we'll have to first import torch, and then let's run it. So then we'll have to specify 2 tensors. So let's say our first tensor, which is x, let it be to 2, and the first function was requires grad equal to true. Okay, we will copy this whole thing, paste it here, and this will be our second one. The value we will initialize as 3. So let's now run it. After that we had a log function, so torch.log, and we multiplied x and y, and we will run this particular cell. After that, the first function was requires grad, the second function was isLeaf. Now if you remember from the slides, which you can see right now, x was leaf and w was a derived function, a derived variable, and hence not a leaf. So to find that out, we can say x dot is leaf. So is underscore leaf, and let's say y also is leaf, and w dot is leaf, and we'll just run it. Now you can see that obviously x and y were leaves, if you remember from the slides, and hence we see true. But w was a derived variable, so it was derived through this operation, log and then multiplication of x and y, so it is not a leaf. Okay, the third function, that was grad function. So in order to do that, we will say, let's say grad w dot grad underscore function, and let's say grad function, and let's run this cell. So you see, if you remember from the graph, w was derived after the log operation. So you can see w is derived from the log operation, which was on another variable, internal variable v. So you have just for the w we will see log backward. Okay, but x was an independent variable, so it will have none as its grad function. Okay, and the last one was grad. So w dot grad and x dot grad. You can also do y. I'll just skip that because x and y are similar. So okay, one thing that I forgot to mention is, right now you are seeing that it is all none and none. The reason for that is we have not run the backward function. So let's say w was our final variable, and we will say w dot backward. Now after that, after running this w dot backward, now if you are going to run this particular cell, you will see a value 0.5. Now if you do your calculations and then try to find out, you will get this particular value as 0.5. This is for x, because x is a leaf node, and hence you need to update the weights for this. Now since w was derived, you don't have to update the weights, and so it is not showing any your value. So if you have any doubts, comment section, Instagram DM. I don't know. I'm not giving my Facebook ID so much. So if I'll try to give my Facebook ID also, and Fiverr. So Fiverr is like, if you don't understand, you need an entire one-to-one discussion, then go there. If you want just one line answer to anything, just go on these other platforms. Mostly I use Instagram. So if you DM, there's a very high probability that I'm going to answer to your questions. So thank you very much. And the next video will be on dataset and data loader, and then we will really pace and finish um, this entire series, because these were the two theoretical and the most important videos. So thank you very much, and bye.